So I'm Naoki Koshimoto from University of Tokyo, and I've been visiting David Bennett in Goddard since last week. So today I'm talking about probable evidence of systematic errors in Spitzer 2015 parallax measurements. We compare the parallax measurements from Spitzer 2015 campaign with the galactic model prediction. And this is a result of it. And we find that measured pi values are too large compared to the galactic model prediction. So why comparing with galactic model? So it is already known that large systematic errors are frequently shown in the Spitzer photometry. This figure from Zhu et al. 2017 is an example of it. And the cyan data points Spitzer right curve, and there is a clear deviation from the single lens event. But actually, the deviation was concluded as systematics in the Spitzer photometry. And there are many other events, many other Spitzer events similar to this case. So it is important to compare the distribution of Spitzer pi measurements and the galactic model to know how much the measurements are affected by such systematics in the photometry. So basic idea for the comparison is this. So microlensing single lens event detection efficiency depends on TE, U naught, Fs, and T naught. So TE is only a parameter which affects both detection efficiency and lens parameters. So once we fix the T values as the observed value, we can fairly compare the model calculate probability of this P-gal pi for fixed TE with an observed pi obs from Spitzer campaign. Here, this P-gal pi is a conditional probability distribution of pi calculated using the galactic model when TE is given as T equal T obs. For such comparison, we need a pure sample which unbiased toward pi values. So we decided to use 50 single lens events from raw sample of Zhu et al. 2017 paper. Zhu et al. 17 is a statistical paper which analyzed 2015 Spitzer events. And their raw sample looks no bias towards pi measurements, so we decided to use it. One problem here is each event has up to 4 degenerate solutions. So we select solutions with minimum value of chi-square R, defined as this formula, that reflects both chi-square and the rich argument of likelihood proportional to pi to minus 2. Here is a visual comparison of the measurements and the galactic model. So black dots are from the pi observed pi values from Zhu et al. Paper, and the color map shows the pi distribution as a function of fixed T values. So please do not compare among the horizontal axis because it's just fixed in each bin. So, and for the galactic model, we use the Zhu et al. 17 galactic model with a typical coordinate of LB equal 1 minus 2.2. And the lines, I need to use this. So, and the lines are the percentiles from top. And for some events, we put I put the percentile values because we use these values for the statistical test later. So for example, this outlier has extremely small percentile of 0.002. And for this one has 0.16 because it is almost on this 16th percentile. And you can see most observed pi values are above the median of the model. So Spitzer parallax is too large compared to the galactic model, even from. This one is a corresponding percentile from top. So here is 2.5 pi. Yeah, so the Spitzer paradox is too large compared to the galactic model. So then we conduct statistical tests because we need quantitative value to know how much the discrepancy is significant. So the idea for that is this one. If pi obs follows p gal pi e for fixed TE, the corresponding pi percentiles at the observed value should be distributed uniformly. So we can do the statistical test using this fact. In tests, to avoid the effect of model selection, we use the following three galactic models: Zhu et al. 17, Sumi et al. 11, and Bennett et al. 14. Here is an example of statistical test. At first, we calculated percentile from top, or this upper probability, pi, for all the 50 events. And the two left panels show the example. And for this event, we calculated the prior pi distribution from the galactic model using this event parameter. And because the observed pi value for this event is here, then the percentile from top is 0.08. And for the bottom one, the percentile is 0.17 in the same way. And then calculate the percentile values for all the 50 events and make the cumulative distribution of it like this black line in the right figure. Then we test if the black line follows the red line of the uniform distribution by using AD test and KS test. We got p-value of 9.1 times 10 to minus 9 for AD test and p-value of 8.8 times 10 to minus 8 for KS test. Actually, AD test is more sensitive than KS test, so we focus on the result of AD test hereafter. So again, p-value is 9.1 times 10 to minus 9, so which is extremely small probability. We conducted the same test with the other two galactic model and had extremely small probability as well. Then we concluded that two distributions are significantly different with all three models. So what makes the discrepancy? Although I skipped the details, we conducted the same test with modifications on the galactic model, or with a different choice of degenerate solutions. But neither of them could help the situation. So we concluded that discrepancy is likely to be caused by systematic errors in pi measurements. So what's the possible sources of systematics? We came up with these three sources listed here, and I will explain it one by one. The first one is systematic errors in the Spitzer photometry itself. As I mentioned at first, it is already known that some Spitzer events has systematic error in the Spitzer right curve. They've counted the number of events showing systematic in Zhu et al. Sample and found that 18 of 50 events show visually identified systematic errors. Here are three examples of this, and actually the right one has prominent deviation from the single lens event. And actually this also has the second smallest pi error bar. And so because the deviation part has large chi-square contribution, then the very small pi error bar could be due to the systematic part, systematics. The second one is systematic errors in the procedure to constrain the source color I minus 3.6 micron. We found that about half of 50 events are not observed over the peaks. And for such events, their pi measurements mostly depend on the source color constraint using color relation. So if there is some problems in the color relation, such as large scatter due to blending or so, it could also lead in incorrect pi measurements. So the last one is the case where the lens or source has a companion, but I skip this because I don't have the time. And finally, we consider the problems as underestimated error bars of pi measurements. It would be better if we increase the error bar of photometry itself, but we couldn't do it. So instead, we increase the error bar of pi with this modified error bars of this formula with new parameter of k and sigma pi mean. Actually, just increasing error bar would not help the situation because the representative value would not change if we just increase the error bar. So we introduce Bayesian analysis to calculate posterior distribution for each event. So for each event, we have a prior distribution from the galactic model. And assuming Gaussian distribution, the black line is observed value. And also posterior distribution multiplying them in blue line. With k equal 1, the posterior distribution is almost same as the observed 1. But with k equals 3, the posterior distribution shifted toward prior distribution, and it could reduce the discrepancy if we increase the error bar. Then we calculated the corresponding percentile distribution to the posterior distribution like this, the thin lines in the top panel in the right figure. And then summing up this distribution and the cumulative distribution on the bottom panel shows the summation of these percentiles. And actually, this is also continuous distribution. So we divide the vertical into 50 because 50 events contribute this cumulative distribution. And then conduct the same test. And this is the resulted p-value as a function of k-value. Even with the minimum requirement of p-value of 0.05, we found that 4 times larger error bar for pi measurements with sigma pi mean equal to 0, or adding minimum pi error bar of 0.05 in quadrature, and then multiplying 1.7 is needed. So here is the summary slide, and although we consider to increase the error bars of pi measurements, probably it would be better to study nature of Spitzer systematics with baseline data of previous Spitzer events, like Yoshi explained it last talk. Thank you.
In your statistics, did you separate the events into 2 groups? One group, for events with a kind of covered, the peak, and another group, in a kind of a segment. So if you do the same test for, applying to the different groups, do you think the statistics will be greatly different? For example, the one on the left, at the third, the left third column, the peak is well covered.
Okay, okay,
Many
yeah.
of them, you know,
Yeah,
the
so actually I didn't do that, but I did the test without five, how to say, outlier events, and then we have very small p-values as well. So yeah.
So, not to be flip, but you know, Bayesian priors have this nice property that if you eliminate all observational constraints, you end up with the prior. And so I think that that's basically what you're doing by increasing k, is you're basically eliminating the constraint on the parallax itself. And of course, then you get a probability of, then you of course recover the input model. So the one thing that you haven't put it in here as something to look at is maybe the model's just wrong.
what model, Bayesian model or what?
Galactic.
A galactic model.
But actually, we had some modifications on the galactic model, and it couldn't help the situation. So if the galactic model is totally wrong, it could be okay. But
One possibility you have, it seems for me, you have not considered is that it's not a error in Spitzer measurement, it's just selection of the events. That, as it was mentioned, when the event peaks for Spitzer sooner than it peaks on Earth, it's possible that when the data are started being collected, the event is already over for Spitzer, and then it's the parallax is not measured. So this way you're producing and you're not including, it seems, this effect in your so-called prior. So this makes problems with the comparison, and I think all such problems are mentioned in Jennifer's 2015 paper. And if that's true, then these discrepancies that are seen do not affect the distribution of galactic distribution of planets.
okay, so actually, I'm not sure if I understand your comment correctly, but I use a sample from Zueto 17th row sample, and I think it very fairly corrects events. So maybe unbiased towards pi measurements. So
that was stimulating, but we're out of time in the question session, and there could be like 5 or 6 more
serious
questions.
problem,
I'm sorry.
you know.
So next up, we're going to hear from
This is a serious problem. Even using Spitzer.
From IPAC, and
the
the talk is Spitzer opens new path to break classic degeneracy for Jupiter mass microlensing planets, and then the planet has a name.
Thanks. So thanks. I'm going to discuss Ogle 171140 from the 2017 Spitzer campaign. This is a Spitzer planet in that it has been observed with Spitzer. It belongs to the Spitzer sample for the analysis of the relative distribution of planet. Contrary to other planets observed with Spitzer, in fact, this time we could fully characterize the binary model just out of Spitzer data, although there is information also in ground-based data. And indeed, from the parallax information that we get comparing Spitzer and ground-based data light curve, we were able to solve an underlying degeneracy to lens to source. And finally, it is also a quite interesting planet in itself, as there are many few other examples for a Microlensing planet being a super-Jupiter mass planet orbiting beyond the system snow line. So this case is a case of, I would say, quite it's a bright and isolated Spitzer target. So you can see that the target is well visible already at baseline, and it is fairly isolated. This data from the 3.6 micron Spitzer camera. The pixels angular size is 1.2 arc second. Telescope in principle should operate in the diffraction limit, but for the 3.6 micron there is some say jitter in the telescope, so that it is slightly beyond that. And the full width at maximum is about 1.7 arc seconds, so that in scattered field photometry does not work as well, but in this case it does. a very critical point for Spitzer analysis that there is a quite strong interpixel effect, so that depending on where the star exactly fall, you have a different response in the pixel. This is why it is very crucial to get a right estimate of the centroid of the pixel of the star. This is what I'm showing here. This is the light curve of the offset from the nominal position from ground-based observation in unit of pixel along the Spitzer observation. So you can see the scatter is very narrow, about 0.04 pixel. So that's excellent for, say, average good events. We get this RMS of order about 1/10 of a pixel, given that the knowledge, the underlying knowledge of the interpixel variation is up to 1/5 of a pixel. So as you can see here, the light curve is the full microlensing variation is covered from baseline to peak, and there is also this anomaly going on here. So Yossi already mentioned, discussed the process of the selection, the idea for an event to belong, for a planetary event to belong, to enter the sample for the statistical analysis is that we should not have a prior knowledge of the presence of the planetary anomaly when we do the selection. Then there are a lot of caveats, which explains why this huge and awkward table that Yossi explained. But in this case, the process was quite straightforward, where the only say trick was that the event was actually announced by the Ogle as a new Ogle event at around noon UT on June 19. It was just 1 hour before the upload, which is done weekly. Then the target, the list of events which are uploaded are going to be observed for 1 week, starting, this is done on Monday, starting the next Thursday to, say, Saturday. So as there was very little time, it was up to the upload team, so basically Andy, to decide to select this event, which he did, fortunately. So this is this 2 line here that you can see here is the Ogle alert, and then here is the time that was the selection. At this time, it was just what we call a secret selection, so that it was not announced, so there was no commitment. But then in the following days, so there were not so many Ogle data points, which are shown here in black, but quite a lot of KMT data, and seeing that the event was indeed rising, and it was expected actually to fulfill the objective criteria by the time of the next upload, which was here 1 week later. It was actually subjectively announced, so there was actually a commitment to observe it on this date, so that actually all data taken afterwards can be used for the analysis. And in any case, as you can see, this is well before the time of the peak where we have the anomaly. So as for the modeling itself, I will come back to the generous with the two-source solution later on. So what we can see is that the anomaly is primarily visible on Spitzer data. Well, this is explained because Spitzer trajectory is clearly closer to the this central resonant caustic than as seen from ground-based data. So Spitzer typically has also in this case have a cadence of about 1 observation per day. So of course we could actually sample this degeneracy because it is a resonant caustic, so it has a typical time scale which is quite long. We could actually completely model through starting with a grid search and then followed by an MCMC analysis. And the binary model just out of Spitzer data, including a constraint on the final size effect rho. From ground-based data, we get basically the same for S and Q, but no constraint on rho. Then out of a joint analysis, well, beside a refined constraint on the SQ and rho, we also get, of course, the Microlens parallax. And in this case, we only have a degeneracy in the direction of the parallax, not in the amplitude, because the other solution was excluded by delta square, I think, about 500. So you can see that the residual are quite flat in all cases, especially for Spitzer. And there is, also from ground, you can see that the anomaly is not quite visible still if you compare to versus a PSPL model, the systematic are quite apparent. So to get to the physical parameter, as we have knowledge of the parallax, what we need is theta e. For this, we need a photometric characterization of the source through the analysis of theta stars, so from the knowledge of the position of the source in the CMD. So we end up with an host mass of it's a M-dwarf of 0.2 solar masses, and therefore being Q of order of 10 to minus 3, there is a 2 Jupiter mass planet, and I recall that for this, using this equation, we don't have any dependence from the source distance. Then, well, the source is clearly a bulge object, and we get an estimate for the projected separation of about 1 AU, namely about twice the system snow line. So the other information that we get is a very small relative parallax, indicating that the length is indeed quite close to the source, suggesting therefore a bulge event. However, in this case, well, we do have additional information. Well, first of all, of course, thanks to the measure of the parallax, we have an information on the relative velocity in terms of as a vectorial quantity. And additionally, thanks to the Ogle 4 dataset spanning along several years, there could be a measure for the source proper motion, so that we can actually solve for the length proper motion. So the length the source proper motion is shown here at the center as the blue dot. Then this is the derived length proper motion, and this is compared to the underlying distribution for the red clump star, which are here in red, which set the underlying reference frame, and then also you have this set of foreground main sequence star. And in this plot, what is shown are the observed, these are the RGB, so the red, bulge star within the field. So as you can see, so out of the two solutions, this one, which is the minus solution, is quite well aligned with the expected galactic rotation, which is traced by main sequence disk star. So we can, so at a glance, we can actually say that the kinematic analysis actually suggests that the event may actually be a disk object. So we also carried out some kind of a more elaborate analysis, but in the end we end up with about a factor of 3 in terms of relative probability, without accounting, however, for any underlying model. So I stress this is just a ratio for the kinematic part of the probability. To end up with the breaking for the 2L versus 2S analysis. So coming back here to the initial light curve, you can see that so what appears to be the anomaly is just, say, 2 peaks. So this is suggestive of the also of the 1L 2S solution. And indeed, if we fit separately ground-based data and also Spitzer data with a 1L 2S model, the resulting residual are quite flat at all. With Spitzer, for which the binary signal is stronger, the chi-square get actually quite worse than what we get for the binary lens solution. However, when we carry out a joint fit, ground plus Spitzer, you can see that we get the residual showing very large systematics, and indeed, of course, correspondingly, the delta chi-square is larger than the sum of these two values, by 6 or 700. So the underlying reason is that, of course, for a binary source model, the two T0 and the two U0 are just independent parameter of the model. They should be the same as observed from Spitzer and from ground. Then if you, we compare these two quantities from Spitzer and from ground, they are clearly different. And so that's also the underlying reason why the parallax is actually telling us that the two source model must be excluded. So I get to the conclusion and take question. Thanks.
All right, questions? David.
So in the previous talk, Naoki referred to the Zhu et al. Paper on the 2015 data.
Mm-hmm.
And there were several events there where there were apparent features in the Spitzer data, and it seemed to be concluded that these were due to systematic errors. In the one case that they discuss explicitly, they say that there aren't binary models that fit both the Spitzer data and the ground-based data. And so I'm wondering if there's a good reason to believe that this signal in the Spitzer data is not due to a systematic error. And if it's if you got 10 of these things and you find only one of them that's consistent with a binary lens model, and you throw out the other ones as due to systematic errors, that's really not a
well, I would agree with this statement. However, I mean, there is, there are difference from, let's say, Spitzer signal and Spitzer signal. In this case, typical problem that, so as I mentioned, there are many potential issues with Spitzer photometry, which are almost always related to problem of crowding. So when we get into, let's say, trouble with the Spitzer photometry, this is often related to having, say, nearby bright or brightest star, also compared, of course, to the brightness of the Spitzer signal. So many cases where we may have actual problem within the photometry fall in this range, whereas in this case we don't. This is also, say, manifest one clear indication for this. In this case, as it's not always the case, we get an extremely well-centered centroid with a very narrow distribution, showing that we actually get a very precise determination of the centroid, and this actually makes us confident that we are getting the correct signal. And overall, the signal-to-noise ratio in this scale here is 20 up to 120. When we may have trouble, say, and then it's the Spitzer photometry we must pay extra care, is when this level is of around 2 or 3 units, very near, let's say, also to the background level. So, say, here we are in a completely different regime, both in terms of, say, source cloudiness and signal-to-noise ratio. So and then of course, in this case, the best proof that for this specific case, the signal, the Spitzer signal is reliable, comes from ground-based data, for which, as I show here, the completely independent analysis carried out with Spitzer and for ground, they result in practically identical model. Well, except of course, as I mentioned, for ground there is no constraint on rho. But that's.
Thank you. We're a little over time, so we'll have to move on to the next talk. We're going to hear from Amber Malthus from
Hi everyone, I'm Amber and I'm from the University of Canterbury, and I am studying for my PhD under the supervision of Michael Albrow. Today I'm going to be talking to you about two low mass binary events that I have, well, one that I've analysed and one that Michael has analysed. And the collaborators for this include the KMT, Ogle and Spitzer teams. So very little is known about the low mass end of the Brown dwarf mass function. For example, hydrodynamic simulations of the hydrodynamic simulations of the collapse of a large star-forming molecular cloud by Bate 2012 found 450 stars and 800 brown dwarfs. Of those, only some of those had masses less than 30 Jupiter masses, and none of them had binary primaries less than 70 Jupiter masses. So a handful of low-mass brown dwarfs have been found using infrared photometry in young clusters. However, the masses for these have to be found through theoretical means using mass luminosity relations, which are dependent on age. Several free-floating planet candidates have been found in microlensing, for example, two events by Moroz 2018. However, these don't rule out hosts at separations greater than 15 AU. So in comparison to our own solar system, that would be approximately beyond about halfway between Saturn and Uranus. So single lens microlensing events are not the greatest way to probe the lower end of the brown dwarf mass function because they are difficult to detect and characterize. However, binary lens events are easier to detect and characterize due to their caustic crossings. These caustic crossings often end up with higher magnifications, and those higher magnifications mean we are more likely to find finite source effects, and therefore the angular source size and the Einstein radius. The high magnification also means that we are more likely to be observed by Spitzer, which increases our chances of getting parallax measurements which break the mass distance degeneracy. I think that's everything. There have been 4 events that have been published with brown dwarf binaries. Low mass brown dwarf binaries, and those are Choi and others 2013, Han and others 2017, and Albrow and others 2018, which I'll be discussing later. But my preliminary analysis of OB171038 finds that this is the 5th low mass brown dwarf binary system. So this here is the ground-based fit. So this is found in the fairly usual method. We use a grid search over the separation, the mass ratio, and the source size to find good regions in the chi-squared space, and then we use MCMC to further narrow down those solutions. The MCMC modeling used here is a modified Morse code, which includes GPU parallelization and Foreman-Mackey's MC, as well as Bennett and Ray's Icarus method for determining magnification, and also hexadecimal approximation, where the finite source effects are not so significant. I think that's everything. Oh, right. So also there are data sets here from 3 different Spitzer sources, but also 2 fields, and also Ogle data. Fitting the magnification model here to the KMT data sets in both V and I gives us the source color and magnitude, which when compared with the red clump allows us to find the intrinsic source color and magnitude for this source. So once we have the intrinsic source color source color and magnitude for the source, we can find a color-color relation between a KMT field and the Spitzer field, which allows us to put a constraint on the reasonable deblended source flux in the Spitzer fit. So when we do our Spitzer fit, we start from a grid-based search across delta beta and delta tau, which is effectively just the difference in U0 and the difference in T0. we use the source flux constraint on the Spitzer model as a prior, and the result in this case was a fairly obvious single solution region for the constrained grid. The minimum in this grid was then used to seed an MC model, and in this model we included parallax from the Earth's orbital motion as well as from the space-based perspective. So this was the best fit from the MC modeling. I mean, it is what it is. So because of the symmetries in the magnification field around the axes, the lens axes, there is always a fourfold degeneracy on parallax solutions, and you can see the fourfold degeneracy here. So up in the upper right panel is the previous solution, and the other solutions were found by estimating how the U0 and T0 values would change and then seeding MC instances from that. We find that they have quite different chi-squared values though, and that the upper right panel is far more likely. The proper motion, looking at the proper motions from these solutions, they indicated here by the dots. The two green ones are the small parallax solutions, and the two purples are the large parallax solution, where the one up on the top right again is the one with the best chi-squared value. This seems to rule out the bottom two solutions, well, not rule them out, but make the bottom two solutions seem more likely. So in combination with the chi-squared value, it seems like the minus plus value is somewhat reasonable. So the masses found from this solution were 20.7 Jupiter masses and 13.8 Jupiter masses, with a separation of 0.6 AU and a distance to the lens of 1.94. I should probably say back here as well. The circles are indicative of 1 sigma expected proper motions based on a disk lens and a bulge source at the distance relating to the distance of the solutions that they're color coordinated with. So for the green solutions, this was more like 90 and 60 masses and a lens distance of about 4.4 kiloparsecs. So another event is the OB 1266 analyzed by Michael, and this is the ground-based solution of that event. It shows two well-resolved peaks as the trajectory crosses a triangular planetary caustic. There are OGLE and KMT datasets here. The modeling for that was done in the same method as the previous one. So in this Spitzer satellite grid, you can see the grid search over delta beta and delta tau that I talked about. And this one also has a constraint on the Spitzer flux. But instead of there being one solution like in the previous one, here there are two obvious solution families in those two regions indicated by the pluses. And these form 8 degenerate parallax solutions, which when we look at these, you can see the caustic diagrams for those. And in this case, because of how the plus Spitzer trajectory, the green plus Spitzer trajectory goes through the center of the central caustic, the two small parallax and the two large parallax solutions end up being really similar. So we end up with effectively 6 solutions with very similar chi-squared values. When we look at the proper motion analysis for this, so it's pretty similar here where the circles relate to the same distances, and I've forgotten which one the dotted lines go with. No, sorry, I haven't. The dotted line goes with the plus plus and the minus minus, and the solid line goes with the plus minus and the minus plus for the yellow versions. So here, the proper motion seems to disfavor the 3 bottom solutions, and so we're left with the 3 top solutions as the most likely. So the solution here is for a 16 Jupiter mass and 12 Jupiter mass lens, which comes from the green family of solutions, and the yellow family is less favored but still can't be ruled out. That has an 8 and 6 Jupiter mass and a 90 and 70 Jupiter mass. So this here is a figure of where our masses fit compared with other published masses for low mass brown dwarfs. And on this, the purple line indicates the deuterium fusion limit, and the blue lines come from Ogle and Moa studies on TE distributions from single lens events. The green bars are representative of planetary bound planetary masses. These are from the NASA Exoplanet Archive, and these mostly include assumptions about host masses. So the top dot, the lone dot, is the rather rare single lens brown dwarf event with finite source effects, and the others are the other published brown dwarf binaries. So here we can see our ones are quite small, but the all-brown one is by far the smallest. But the most important thing here is that there seems to be an overlap between the planetary masses and the brown dwarf masses. And this raises an important issue for characterizing these things, because if we don't know anything about the formation method of them, how can we possibly say whether or not something is a free-floating planet or a very low-mass brown dwarf? So we can see quite clearly that all of these things exist in binaries at that mass, and so therefore it's pretty easy to assume that they will also exist in singular, and so free-floating planets may in fact actually just be low-mass binaries and without knowledge of their formation. That's a bit hard to characterize. Okay, that's all.
Thank you for finishing on time. That's good. Questions?
Hi.
Hi, Scott.
I think there's at least one more single free-floating brown dwarf.
Apologies.
Which is Gould et al.
2009, but
Is it very low though? Because sorry, I was specifically trying to talk about very low masses, but
How
I
low
might have
mass?
forgotten
I
to
think this one
mention that.
was 40.
That may have been too high. What was?
it's 0.05 solar masses.
Okay.
Oh, so it's too
Yeah,
high.
I think that was probably just always like a random arbitrary distinction between low mass and not low mass brown dwarfs. Yes, Andy?
Could you put your plot back of the proper motion circles and crosses?
For which event?
What?
This event or the other one?
Other one.
The other one.
The one you were just working on that recently.
Yeah.
Yeah. So you know, the Gaia proper motion of the source, you know, is -5 in north and -7 in -8 in east.
Yep, so that will change where those circles end up, but I haven't had a chance to do that analysis yet, sorry.
But anyway, it's I think it does tend to agree with that, the green point.
Okay.
I mean, you know, it could be still produced by peculiar motion of the lens, but it's going that way.
It certainly could. The preliminary results, it could well be a 90 and 70 mass lens. Jupiter mass.
Let's see.
So I just want to point, can you go back to your final slide?
Yeah.
You said that the Deuterium limit as like the limit for planets, but I actually think that,
not really.
these two like brown dwarf binaries actually the key to show that this is not really the limit, and these are probably formed like binaries, and with that the definition of a planet is actually probably more related to a mass ratio and not to an absolute mass.
Yeah, that's fair. I'm sorry if I misspoke somewhere in that. I'm not sure what I said about it. The deuterium limit I meant is often used to determine a difference, but it certainly isn't.
It's not a comment against, it's a comment in favor.
Okay, cool. Anyone else? Yes.
And for the next talk, we'll hear from Radek Pileski from Ohio State University on K2 Campaign 9 data analysis of another microlensing event with the name.
Oh, thank you. Yeah, so I'm Radek Pileski from Ohio State, and I'll be talking about K2 and some particular planetary event. So when it comes first to K2 and K2 campaign 9, it was first space-based microlensing survey. Survey meaning a patch of the sky was observed continuously, and we did not need any alerts from the ground to get the data from the space. So in principle, this allowed measuring or constraining masses of a bunch of objects, including, most importantly, of free-floating planets. Unfortunately, the survey was conducted with the telescope that was unstable, had unstable pointing. So the telescope moves all the time. During every exposure, it moves back and forth. Sorry, maybe not back and forth, but it moves all the time. And pixels are large, 4 arc seconds on a side. So that's not good when you're looking at the dense field of galactic bulge. And finally, there were some technical problems that delayed the start of campaign. And we'll see that at the end of my talk that they turn out to be important. So we wanted to analyze some planetary event very fast, and we've seen anomalous event even before K2 campaign 9 started. So here's first model, I think, circulated to the community by Valerio. We clearly can see that the event is anomalous, and it's before the campaign starts, so everybody was excited to have, for sure, a planet from K2 experiment. Here's model by Yuki Hirao with more data, and it basically shows the how these binary lens models look like. So we have this caustic and the source. Later on, we've seen that it rather moves off the caustic. It doesn't cross the caustic, but it's very similar to what we see here. And I think that's the final model circulated by Valerio in August 2016. And Valerio, while circulating this model, pointed out that there are significant residuals. So most probably, in his opinion, there were some problems with the data. So he asked people to re-reduce their data so that the model fits better. So nowadays, I collected all the information we have for this event. So as you can see, here's a list of all the data sets that I got. Thank you for everybody who contributed to collecting those data. I think like 1/3 of the room contributed. So there's really lots of data. So that's good. I'm analyzing this event using software called Mulens model. It's public code. If you want to use it, just goes to the GitHub website. There's also documentation. Every function is well documented. The code is fully public. There's a paper by me and Jennifer Yee that describes the code. If you want to use it or you're using it and have some questions, just ask me or shoot me an email. And I'd like to advertise somehow this code. So like if somebody advertised a movie, then they quote somebody from like some famous movie critic, that watched the movie and said something good about the movie. I haven't found microlensing software critic, but I recently got an email which said it's such a wonderful resource, and the email was sent by anonymous astronomer Kalen H. Yeah, maybe some of you know him. So if you have questions about the code, ask me whenever you want. So here's all the data that we have from the ground for this particular event, and I'm also showing static binary lens model. It's hard to see the model itself because it's under all of these data points. You see there are lots of colors, so it's really nicely looking plot, except that it's very hard to read anything from that plot because of the number of colors. So in later plots, I'm removing all the follow-up, and that's because 3 surveys contribute most to the constraints on the model, but I'm using all of the existing data in the feeds. I'm just not showing them on the further plots. So to make it easier, just 5 colors for 5 different data sets, Ogle, Mo, and 3 KMT data sets, and that's the light curve of the full event. And when you look at that, you see that there are still residuals, and they're significant. It's not just like one night that some telescope was bad or something, and they're there even though we're using data from different telescopes independently reduced. So of course, if you approach that and you try to fit your model well and it doesn't fit, then you add additional higher order effects. So of course, you add limb darkening, that's easy. Then you add microlensing parallax.
it didn't help much, to be honest. Then I added orbital motion of the lens because that's like the next higher order effect we know. And still, to be honest, nothing helped. The residuals look basically the same, no matter how much more complicated I made the model. So then the idea was, let's do something different. So here's static binary source model, not binary lens, but binary source model. So Martin was asking where are all the binary source events. Here's the one. When we look at the residuals, they're almost flat. Yeah, you see it's very nice improvement over the previous model, and both the main peak, that is anomalous, and the SNE were described by the binary source model. So the best candidate for being K2 campaign 9 planetary event is killed, in the sense it's not planetary. Sorry. When it comes to K2, analyzing K2 photometry is not easy. So what I'm doing is a method that started first with Dan Wang's causal pixel model. So here we have signal that is seen in one of the K2 pixels. And this scatter that you see is well correlated between different pixels. So Dan's idea was to decompose it and relate to signals that are seen in other pixels. So the signal seen in this pixel is some linear combination of signals seen in other pixels. And as you can see, these patterns are quite similar. There are really good similarities between them. So that somehow helps. So he used basically this equation in slightly different form, but the signal observed in given pixel at pixel M at epoch I is equal to some linear combination of signals seen in other pixels, but at the same epoch plus some residuals. So I modified this, and it took me some time. Finally, I arrived in slightly more complicated equation. So in simple form, it's observed signal minus microlensing signal times the PRF, that pixel response function calculated for given source and given pixels for given epoch, equals this instrumental trends plus some residuals. So if you like equations in more formal way, here's the equation. So this is what I'm taking from Dan's method. I'm adding this PRF and K2 source flux and the microlensing magnification. So in my method, I'm extracting these source fluxes and magnifications, and I'm in order to do that, I have to assume the magnification, so it's simultaneous model fitting and photometry extraction. There's many details to the method. I won't go into them. The code that uses this method is public. The paper is under review, and I think the last missing point is estimating the K2 source flux based on ground-based fluxes measured in different bands, and that's what I'm now working on. So how K2 data look like for this event? They look like that. So the K2 started taking data here, even though it was supposed to start taking data somewhere here. So without this technical delay at the beginning of the mission, we would cut the peak or close to the peak, or at least the peak produced by the second source, which is somewhere here. They even get faint, so there are significant residuals. And in this case, since we did not cut the peak, the parallax measurement is affected by the source flux measurement, because there's degeneracy between the parallax, north component of the parallax, and the source flux. So I'm still working on that. So to sum up, the title of my talk was wrong. OB 160241 is not a planetary event, it's binary source event. I have the method that is good for extracting K2 C9 photometry. And following Martin's comments, I encourage everybody to check binary source models, not only binary lens models, in which we're mostly interested in. Thank you.
Thank you for finishing on time.
Can you use your seat mic, please?
Yeah, okay. Did you see some color effect on the peak due to various data set that could explain the binary source model better than the binary less and give you the clue that the true model was a binary source?
To be honest, I haven't checked that, and mostly on the main peak, the data are from MOA survey. So maybe I'll go back one more.
Okay.
Yeah, but for oops, is it? No, it's later. Yeah. So the flux ratio between the two sources doesn't change much between the different bands. So I checked that. I don't remember the exact numbers right now. Michael?
I noticed you didn't explicitly put a blend flux in the model. Is there a constant term in the eigenfunctions
also? You mean in the K2 extraction method? Yes. So any additive constant is removed, and I did check that. So I also made a fits with just adding this constant, and the method converged to this additional flux being equal to 0. And this decorrelation removes any constant flux.
Additional questions?
Andy.
So you said that you encourage people to look for binary sources, but it took you a very long time to look for it yourself. But why is that? Because it's just not part of general culture.
Maybe, yeah, and like I knew I have to do this before submitting the paper, but like it was later, and yeah, once I've checked, it's soon converged to a really good model. So, yeah.
All right. Well, thank you, Radek.
Hello? Hello? All right, okay, sorry, I changed my talk topic. I'm going to instead talk about galactic models for Bayesian analysis, but presupposing that Spitzer solutions are correct. So I smell some gunpowder in the room, but I'm sure no matter which camp you're on, this talk will be of interest to you, hopefully. All right, so I think it would be great if we can send Spitzer after every event that we detect, but that's of course wishful thinking. Of all the microlensing planets we detected so far, only 5 or maybe 8 now have Spitzer parallax. This means most lenses have not and will not be characterized by satellite parallax. Which means instead we have to study them with Bayesian analysis. Quick reminder of how this works. You observe an event, you measure its TE and theta E, that becomes your input that you shove into this machinery here, which generates a bunch of trial events in the form of lens-source pairs from some galactic model with these ingredients. And your properties of the lenses in your simulated events gets weighted by how well they compare to the TE and theta E of your actual event. And that becomes your posterior for your lens properties. So this overall framework is pretty typical, but what the machinery contains exactly is not necessarily standard. People make different choices for the ingredients in the galactic model. How does that change their conclusions, if at all? Well, let's say I use the galactic model choices, typical for our group. I'll call it the baseline model. For this event, 161195, which is a planetary lens, I get these posteriors for my stellar mass, host mass. The yellow shaded region is the 68% confidence intervals. And we can see it looks like the star is most likely about 0.2 solar masses. Sorry, the tick marks are bad. But actually, another group has already Bayes analyzed this event. These are the solution from Bond et al., shaded in blue. And you can see that they're 1 sigma off almost from our results. Now, of course, this group uses a different galactic model, and Bayesian inference by definition depends on your prior. But you might expect similarly reasonable priors should get you similar results. And hopefully that's true when we're studying an ensemble of lenses put together by different, or published by different groups. So this sort of discrepancy should make us a little bit nervous. Here's something else to make us nervous. This happens to be a Spitzer lens studied by Schwarzwald et al. Their results are plotted in this maroon dotted line all the way here. And just for reference, these are the distance plot. That's the distance plot, sorry. So what's happening here? This is interesting, right? It shows that in this case, the common galactic models that we're using are failing to reproduce accurate lens properties. Now, to be fair, I've shown you just one object, and this one actually also happens to be kinematically peculiar. So maybe we shouldn't read too much into this. Let's look at another object. 140962 is a binary, Spitzer binary that we characterized. Bayesian analysis with our baseline model shows that the primary mass is consistent with a brown dwarf, which means this might be a brown dwarf binary that we heard about earlier. But Spitzer parallax tells us a different story. It says the lens system is really just a mid-M dwarf stellar binary. So here again, the Spitzer results are about a sigma off from our posteriors. Okay, maybe we're getting a little uncomfortable. Maybe we want to take a systematic look at how galactic models we're using for Bayesian analysis are doing. Right? Are they representing the true lens properties fairly? Sorry, these are the distance plus. Sorry. And to do this, we've set up a little experiment where we tested a couple simple galactic models with Spitzer lenses. So one of the first model choices we had to make was for the mass function. For this, we picked the Chabrier single star mass function, although Krupa and Sumi are also popular. We've included stellar remnants, so not for systems with planets, and we decided to exclude free-floating planet hosts because we think for Spitzer events they should make negligible impact. But in a more comprehensive study, we might choose to test more mass functions, but as this plot actually shows, what you choose doesn't make too much of a difference. The difference between a Chabrier in black and Sumi in red is about 0.1 dex, which is similar to the difference between having and not having stellar remnants. So for the purpose of this exercise, we're just using one mass function for all the models. We do consider two density functions for the disk and the bulge. One is based on Han and Gould, 1995 and 2003, and the references that they quote, plus scaling factors from later works. So that's plotted in the solid line here. The blue is disk, red is bulge, and black is the sum of the two. And this is plotted in the direction Bottas window. The dash profiles are the model used by Zhou et al. 2017, which you heard from earlier. That has a bulge profile based on Robin et al. 2003. So you notice that the two models have quite different bulge to disk density contrasts. Here are the velocity distributions. We use the same two models from these two references. These plots are just showing how the stars are moving on the left in the direction of galactic rotation, and on the right, galactic pole. So you can see that the two models use quite similar velocity, disk velocities in the blue and different bulge dispersions. So we can permutate the two models and get four toy models. The first model uses purely the Han and Gould model, which is in fact our baseline model. Number 2 and 3 just swap out the density and velocity profiles for Zhu, and number 4 uses just the Zhu. And the idea here is we're going to do Bayesian analysis on with these models on these Spitzer lenses. We hide the parallax information in each case, and we see how close we get to the Spitzer answers, which we're going to call the true answers. So let's see how they compare. This plot is showing on the x-axis the lens primary mass as inferred by Spitzer parallax, and on the y-axis we have the Bayes result, the Bayes inferred masses. So you can see for the baseline model, there are some scatter, but overall they line up pretty well on the one-to-one line. Right. If we swap out the Han and Gould for the Zhu density profile, we can see there's some tightening up here, a bit more scatter down here, but overall not too bad. For the Zhu velocity profile, we see that some of the points have snapped back a little bit to the first model that we saw. And that may be not too surprising because the velocity profiles are fairly similar. And this is the fourth model that I presented. So it's maybe a little hard to assess the comparison visually from the plots earlier. So here's the following. The following is the metric, that we're going to use. On the left, I'm plotting the cumulative distribution function of the fraction of posterior from each model for each lens lying above the Spitzer true answers. And so the idea here is that if your posteriors are representing your lens properties fairly, then you should expect these CDFs to line up with this one-to-one function. One-to-one line. So like 10% of your objects should have 10% of their posteriors lying above the true values. Okay? And the KS test tells us, at least formally, that all these functions are statistically consistent with the one-to-one density function. So at least by this metric, it looks like all the models are doing quite well. But there are definitely systematics that exist between using different models. So here in this plot, I'm showing that if we compare the lens properties we get from the Zhu density profile versus Han and Gould, the lens mass and distances tend to be larger in the Zhu model, density model, for lenses that appear to be farther away. And we think this has to do with, remember, the higher and peakier bulge density profile from Zhu, which tends to pull the lenses that appear already closer to the bulge even closer in. And in any case, I think it's important to be aware that your model choice does affect your lens properties, especially when that effect is systematic like this. So I think correctly interpreting microlensing data is obviously dependent on accurate galactic models, but conversely, that also means that we can use microlensing data to help us constrain models for galactic structure and kinematics. And so you've seen earlier people have done this by comparing observed optical depth and event rate maps to the predictions from galactic models. And I think with this growing Spitzer data set that we have, there's another possible path forward that may complement these other methods. The idea is that how well the lens properties match with predictions from your model is a diagnostic for how reasonable that model is. And so I think it would be really interesting to repeat the test that we did with the bigger sample of Spitzer lenses. And that way we can get better statistics, higher resolution. Let's try to tease out more trends and finer features. So I'm just out of time. I'll leave up my conclusions here. And yeah.
All right, very good talk. And looks like there's many questions. There's somebody behind the pillar. Yes, sorry.
Yeah, so I was wondering if you've Sorry, right
Oh,
here.
okay. Hi.
I was wondering if you've given any thought to marginalizing over the models instead of doing some of that comparison, like direct model to model comparison. So you could like loop that in a reversible jump MCMC type sampling to where you're now hopping between the models as you're doing your other fits in your Bayesian analysis.
You mean combining the models? Sorry, I'm not sure I understand.
So you're sampling the models the same way that you sample the parameters, basically.
Oh, okay. I think okay. I haven't given that any thought yet, but if you think that's the way forward, we should talk afterwards.
Okay, sure.
Yeah.
So this is more like a comment to the previous talk, but also related to this one. So the previous analysis, sorry, Naki, and they found some disagreement between the model and the Bayes estimates from parallax, and they thought that systematics in the Spitzer data, and here you found your Bayes analysis results agree with the galactic model. So my comment to that difference is this clearly shows there is a selection bias in the pi measurement, and therefore, well, okay. So the point to that is if you don't have a bias towards parallax, then 2/3 of the microlensing event should be coming from galactic bars. And because of this selection bias, our analysis shows 2/3 of the microlensing or the Spitzer microlensing events are coming from the galactic disk. So that's the difference, and therefore there is a bias, and therefore of course, there are some systematics in individual Spitzer events, but I don't think that's the issue that is causing the difference in this previous analysis.
I think we did give a little bit thought as to how the sample biases might affect a test like this. And I think you're right. If the sample is inherently not representing the prior assumptions of our galactic model, then that could be a problem. But I also think that because we're inputting for these Bayesian analyses already the TE and theta, the observables for the events, that should somehow inform the galactic models or the Bayesian analysis to kind of probe that the part of that parameter space that that agrees with the observables. I think you do have a little bit of constraint already over. Oh, that makes sense. But we can talk afterwards.
So one thing I don't think you mentioned was that there is an assumption that's made often in these Bayesian analysis, which has to do with the distance distribution of the source stars in the bulge. And so traditionally people have used like some semi-arbitrary power law to weight the stars toward the foreground. And the proper way to do it would be pretty complicated because it would involve actually matching the number of stars you expect to be at the source brightness, which is different for different brightnesses of sources, and it can be a big effect if you're close to a place where the gradient of the brightness distribution is large. But it seems to me that that can have a pretty big effect on these results. And have you look to see that those different models are using the
We
similar
have not explored this issue yet, but we're aware that that is an issue. And something I didn't mention, I guess, when I talked about in the very beginning, the different choices people make for what they include in the machinery is that there are also inherent ways in which people are doing Bayesian analysis that may be different. For instance, as you say, some people weigh the source distance function by a power law, and others do it with a more rigorous kind, I guess, somehow, a brightness function. So I think that's definitely something we need to explore in the future. This is, of course, a very simplistic first step into into exploring Bayesian frameworks for microlensing, but absolutely in the future we should explore that.
Thank you. Great talk and great answers. Up next, Master Kenny of
There we go. Yeah, there we go. Sorry about that. So yeah, I'm going to be talking about the CFHT observations that we've done over the past few years. I should point out that people involved, the Tsinghua group, Pascal Fouquet, Wei Zhu, and then others such as Annie Gould, Yotzi, have provided very good input as well. So a lot of the work I'll be talking about has been done by Wei-Cheng Zhang, who will give the talk after me, so I won't give him any more introduction. So the 2016 observations that we did were the first that we proposed, and they were to support the K2 Campaign 9 microlensing survey. So the idea was that free-floating planets that Kepler will be able to see will generally be very high magnification. But because of the large separation between Kepler and the Earth, the events that would be seen from the Earth would probably have low magnifications. And because Kepler has a very wide bandpath and hard to characterize blending, we'd need to know the color of those events very well, the source colors. And so for very low magnification and possibly faint events, you need bigger glass than the microlensing surveys themselves would be able to provide. So we proposed to CFHT and got a very nice allocation of 27 hours to do this. Our observations were over 90 days. But only during times when the megacam, the wide 1 square degree camera were on telescope. We covered 6 fields and observed in 3 different filters, GR and I, 2 or 3 times per night. And we ended up getting light curves for 217 events in and around the K2 superstamp. And we've also analyzed our reference images and calibrated them to the Pan-STARRS Heart-Full Sky survey, which itself has been very well calibrated, and we've got about 28 million point source detections in our reference image catalogs. So the data, these light curves, the calibrations, etc., are all described in Zhang et al. The data is all public. You can go and use it. And there are links up here, and I'll put a link in the summary slide as well. So this is an example of one of the light curves that we put in the paper. You can see, so the larger points here are the CFHT data compared to the sum of the ground-based survey data. And you can see we get very good quality. And then next to it is the source color measurement for this event on the CMD that we measure. And so these CMDs are really good quality. And the light curves are good quality because CFHT can get better seeing than is achievable from any other site. So if you look closely at these 2 images, so Ogle does the best of the surveys in terms of resolution, but you can see many more stars in the color CFHT image here. And so this allows us to go really, really deep in terms of CMDs. And the fact that we're not just observing in 2 colors, but 3, R-band particularly, means that even in high extinction regions, we can get very good measurements of the red clump. So in addition to providing the data, we also provide some useful tools. So one is a transformation equation to convert between our calibrated magnitudes and the K2, the Kepler filter. And also, in case they're useful, we've provided color angular diameter relations too. So Radek has talked about his K2 analysis, but we've provided the data for some of that, and on the right here is an example from Wei's analysis. So in each case, our source colors are constraining the source flux for these fits. I hoped Radek would talk about the differences between these two, but he hasn't, but ask him about it later. So in addition to the K2 light curves, we provided some useful data for free planetary events in 2016. In particular, we got some very good, very critical data on MOA 2016 bulge 227. It's hard to see on these plots because the error bars are so small. But yeah, so in particular, we constrain one of the Corsic features. Now on to 2018. So I had less of a role. Wei Chang PI'd Vit's proposal and has done most of the preparation and analysis so far. So the 2018 survey had a completely similar goal, but different technique. So rather than trying to help K2 measure parallaxes, it was to try and help Spitzer measure parallaxes. And in particular, to try and aid target selection. So the strategy was to target a wider area and reduce the data quickly to provide feedback into the target selection. And so we had low cadence observations in May, and then we're going to steadily increase the, we've got nothing there. Steadily increase the cadence into June and July before the Spitzer campaign. But unfortunately, the weather for Mauna Kea was terrible last year. So we lost most of the observations we'd have taken in July, and either from the bad weather during the MegaCam run or just from the pressure from other proposals. And so we switched our August observations just to do targeted follow-up of events and get the most that we could out of the time that we've been awarded. But the good news is the real-time pipeline that we developed for this works well, and we'll employ it again this year. So in addition to just to light curves, the good seeing allows us to resolve out blending in events. So this is one example where we used it for a 2017 event. And so just from photometry of the now reasonably resolved the baseline object in 2016, we can place constraints on the blend and therefore the lens flux as well to be due to the difference between the blend and the source, which is in blue. And so this is compared to the Bayesian lens property estimate, which is this orange error bar. So we're ruling out solutions that are above our data point there. In addition, we can do more than just photometry with our data. So we can do astrometry and try and pinpoint where exactly the blended light is to see if it's coincident with the microlensing event. So this is an astrometric analysis of a 2018 event. I won't go into details, but I'll just tell you about the astrometric accuracy that we're achieving. So between two CFHT images, we're managing to get an astrometric precision of about 7 milliarc seconds, between two 20-second images, and we can improve on that with co-addition or averaging. So that's 2018. What are our plans for the future? I've only got 2 minutes left. But again, our goal is to try and improve mass measurements in microlensing. So we've been increasingly discussing the mass ratio distribution, and whenever I try to talk about this with people outside of microlensing, they want to know what the mass distribution is. And so we don't have many direct mass measurements for the planets that are going into these. And part of the reason is we don't have parallaxes for many of the events. So Spitzer can get parallaxes for some new planets each year, but there's many, especially with the high cadence surveys, KMT, Ogle, and MOA in their latest iterations, are able to find planets in events with very faint source magnitudes. And so that's challenging for Spitzer itself, but it also means annual parallax is difficult in those events as well. So if we can provide, with a higher resolution, we can dig into the background and hope to push our abilities to measure annual parallax further into this source magnitude distribution. So in 2016, we'll have two goals. So one is to, again, support Spitzer, and then the second goal will be to do this, to make these annual parallax measurements. And just to really make this point, so this is a prediction of the precision that you can get from the KMT and Ogle compared to what CFHT can do at faint magnitudes with single exposures. So in the past, we've been using 20-second exposures. We can, for only, because of overheads, we can quadruple that time for only half the cost. And then because CFHT is Q-managed observations, if we can make the case that we really need for the best seeing images, we can target our observations to only be taken when the conditions are good. And so if we can do that, we can achieve a factor of 3 to 4 improvement in precision per point compared to the regular microlensing survey observations, where only roughly a factor of 2 of that is coming from the larger diameter of the telescope. And so just to make, so a factor of 3 or 4 in precision, you get to square that in terms of information. And so from tens of data points from CFHT, you can get the equivalent information of several hundred data points from the survey, the regular microlensing surveys. I'm out of time, so I will go to the summary and answer any questions.
David?
So an additional advantage of CFHT observations is sort of more precise characterizations of the colors of the faint sources. And that's really helpful for high angular resolution follow-up observations, because the faint sources are generally the ones where it's easier to resolve the lens star. And so that's like another justification you can use in your proposal.
Thank you.
So why didn't you use 80-second exposures in the first place? What's the advantage of 20 seconds?
So initially we'd just scaled them to roughly match scaled the aperture to match the precision that Ogle and such would get. We knew we'd get slightly better, but we didn't want to saturate. Initially we designed it to support K2, so we didn't want to oversaturate bright things. But now we might as well go deep.
Thank you. Near the end of the day. Thank you, Matt. As advertised by Matt Penny, is Wei Zhang. Okay, I heard you. LCO follow-up for Spitzer and KMT net.
Okay, it's my great pleasure to give a talk about the LCO follow-up for Spitzer and the CAMT-NET events. I'm Wei Zhang, second-year PhD student from Tsinghua University. My supervisor is Professor Shu Mao. And I joined the LCO follow-up group last year, and I must say first say thanks to Yossi, Jennifer, and Andy for teaching me how to follow up and analyze event. And I also must say thanks to Rachel for the support of LCO network and software. Okay, this is the outline for my talk. First, I will answer the basic question, why do we need follow-up observations? Then I will introduce the LCO network and what events did we observe. I will also review the main result in 2017 and 2018. Finally, is our future plan. The typical timescale for a microlensing event is about 20 days, so daily cadence is sufficient to discover microlensing events. However, for planet events, the duration for planet signal is about 1 day for Jupiter mass planet and about several hours for Earth mass planets. So it requires about 1 hour cadence for the to detect Neptune mass planet and about 15 cadence to discover Earth. Moe and Ogo first conducted high cadence observations toward the bulge. And camping now is observation about 12 square degree with a cadence about 15 minutes or 10 minutes, making it no need for follow-up observations. But for most of our other field, there are also need follow-up observations to detect more planets and more smaller planets.
Just take a minute. I'll see if they can bring it back.
Okay, that's okay.
You're the last speaker, so if you just wait.
No, okay. And also, in some cases, the event will be very bright, and the surface image may be saturated. And also, follow-up observation can provide observation at a different size if the surface is affected by poor weather. LCO is a great network for follow-up observations. It has 1 meter and 0.4 meter telescope at the same size with CAMT-NET, CTIO, SAO, and SSO. It can provide very high cadence follow-up observations. In some cases, the cadence can reach 5 minutes. Also, thanks to the software Tom developed by LCOGT, and we can schedule and get observations in 15 minutes. Finally, I developed a fast DIA pipeline based on ICE's package, and it can reduce the image within 5 minutes when the image were taken. So the main purpose for LCO project in 2017 and 2018 is to observe Spitzer events to capture more planet events for Spitzer. So what is the event we observed? First is Moe or Ogo or Moe only events without CAMT observations. We will schedule daily cadence to monitor it, and if we find anomaly, we will increase the cadence. Second is brightening events, also known as Hollywood events, which has great sensitivity to planet. And most of the events we observed are high magnification events. It has excellent sensitivity to planets simply because the source passes very close to the host, where each planet has a caustic. Finally, is some anomaly events. If an event show clear deviation from the single lens model, we will try to capture the caustic exist. So in the past 2 years, we captured 3 planets in total. One in 2017, and 2 in 2018. The events 0406 and 1185 are both high magnification events and located in KMT 15 milli cadence field. But we still observe it because to avoid the surface image were saturated because of the brightness. And the event 0799 is an anomalous event. And the planet signal occurs 4 days after the peak. And the Kelvin cadence is only about 0.4. 0.4, and so our follow-up observations are very important. So this is a plot of the planet signal. There are 3 possible planet models. One is resonant caustic, and another 2 are white planets. So finally, model A is preferred by the data chi-square larger than 50. The most of the data chi-square is based on MOI and LCO data. So this event is also a good case to show the progress we have. And at the morning of 8300, Jennifer alerted this event as a normal event. And then I schedule very dense observation for this event. But finally, you can see we only got less than 10 data points each site each day. It is because we have to compete with other LCO proposals. And in 2016, the 1 meter telescope were always overloaded, and we only got about 30% images we request. And also at the night of 8300, the 1 meter telescope at the SSO were extremely overloaded. So I observed this event by 0.4 meter telescope, but the light curve was flagged. And finally, we find the brightness limited for 0.4 meter telescope is about 16 magnitude. Also, the biggest problem is more than 50% 0.4 meter images we got have tracking or focusing problem. So when tracking the high magnification event, we also observed a lot of finite source events, 4 in 2017 and maybe 7 or 8 in 2018. We can do measurements, we can do mass and distance measurements for isolated objects by financial effects and speed parallax. And from 2015 to 2017, we observed observed 8 financial effects events, 8 in total, which yielding the apparent frequency is about 2.4%, which is agrees the theoretical frequency in Wei Zhu's paper. However, Spitzer only detect financial effect for 2 events among the 8 events. This is simply because the Spitzer observation has 3 to 10 days delay after the event selection. We also compare the mass and distance distribution for these 8 events, which agree with the Glider model. More financial events are in the guide bulge. And also, we have not detected any low mass brown dwarf in the guide bulge. This is also because the delay of the speed of observations, because the time scale of that event is very short. So for the future, in 2019, we are also observe speeder events. This is our main project. And about 1 month later, we will start LCO KMT project based on the KMT real-time alert system. KMT is now having its own early warning system, and it will update the web page per day. More importantly, CamTnet will update its photometry in the website maybe about 12 hours delay after the image were taken. In some cases, the delay will only about 6 or 5 hours. This is a good case to show the importance of follow-up CamT-only events. And without the follow-up, we'll see this event might be a single-length event, although with some anomaly. Based on the CamT data, CamT real-time data, I found this event could be a high magnification event 2 days before the peak, and 1 day before the peak. Based on the latest 2 CamTS data, I found this should be a normal event. As Andy said this morning, high magnification event can be used to study planet multiplicity function. So the future of our project is to focus on high magnification event to study planet multiplicity function. This is a summary. That's all.
Thank you. So are there questions for this last talk today?
So the problems with the 0.4 meter telescopes can't be combated with longer exposures?
No. We use the longest the exposure time we have, 3,000 seconds.
3,000 seconds?
300. Okay. You can see for this event, I scheduled 5 minutes cadence SAO here for 0.4 meter telescope, but all the image has focusing problem, so I have no data at acoustic entry. And the next day, the 0.4 meter image from SAO was very good. So I don't know the reason about it.
Yossi? No? Okay. Would anybody like to ask the last question of the day? Or we could